Hello everyone, I'm Chandi Muyanage from Cybernet Systems, and it's my pleasure to take you through the contents of today's webinar. Now, I think we all agree that COVID is becoming a bit of an old topic and it has become a part of our daily life, otherwise known as the new normal. We are heavily relying on preventive measures to this date. We need to know how effective these measures are, and that's how this topic is still relevant. Before I go to the main topic, let me briefly introduce our group company. Cybernet Malaysia is a fully owned subsidiary of Cybernet Systems Company Limited, headquartered in Tokyo, Japan. Established 37 years ago in 1985, our partnership with Ansys also has a very long history. We have two other sales subsidiaries in China and Taiwan. You may also have heard about Sigmetrix, MapleSoft, and Ansys solutions. They are also actually a part of the Cybernet group. Cybernet Systems Malaysia is a channel partner of Ansys for the countries in the ASEAN region. We are specialized in CA solutions, digital transformation, and we also provide engineering services, training, and consultation in those domains. Today's presentation material and analysis examples were originally created by the CA business unit of Cybernet Systems Japan. I'd like to thank them for providing the original content. Ansys software used in this presentation are mainly the CFD products. Let's move on to the main topic for today. We will show you a number of analysis examples for visualization of the effectiveness of COVID-19 preventive measures, including wearing masks, spray washing, sterilization, etc. Please note that the simulation examples included in this presentation were computer generated under specific circumstances, and these are not intended to provide medical advice or guidance. Environmental variables such as wind and humidity were not taken into account during some of these simulations as well. The purpose of today's webinar is to introduce simulation case studies related to COVID-19 countermeasures. Like the one on the bottom right, that is something we can easily relate to. There are two human models and the wind is blowing from the left side. When droplets are sprayed from the mouth of the model on the left, how will the droplets reach to the model on the right? And how will the surrounding wind affect the way the droplets spread? We're going to look at several examples like this in detail. We have received a lot of inquiries regarding simulations of COVID-19 countermeasures. So we hope that these case studies will give you an idea on how to utilize simulations for your own products. During this webinar, we will focus especially on CFD, Computer Fluid Dynamic Simulation, using Ansys CFD products. I will also discuss later a little bit about why CFD plays an important role on fighting COVID-19 and the new normal. Here's the agenda for today's webinar. We have two main topics. Firstly, we will briefly explain why CFD is useful for fighting COVID-19. And secondly, we will show you a number of case studies, which is actually the main objective of this webinar. So why CFD is useful for fighting COVID-19? CFD allows us to visualize something that is invisible. For example, it's possible to color the flow and direction of the wind and to represent viruses and droplets as particles. This example visualizes ventilation in an aircraft. You can see how air flows in from the top and spreads throughout the aircraft. Just like this, CFD makes it possible to color the flow and direction of the wind, which is impossible to see otherwise. Also, as shown in the example on bottom right, by representing viruses and droplets as particles, it's possible to observe where the particles will attach on the surface of the human body model. In addition, CFD is risk-free. This is actually true not only for CFD, but for simulation technology in general. For example, verification involving explosions is dangerous in a physical experiment. But in the case of simulation, this experiment is conducted in virtual space on a computer, so it can be done safely. In the same way, a verification that involves the spread of a virus or other highly hazardous material can be done safely. Let's look at some examples of real-life applications. This one is from Japan Railways and the Railway Research Institute in Japan. The illustration on the left shows the ventilation inside a commuter train. It says that by opening the windows for about 5 to 10 centimeters, the air inside the train will be replaced every 6 to 8 minutes. You can see that this observation is based on numerical simulation by using CFD analysis. Here's another practical example, and this one is of a toilet. The bottom right picture is an example of a toilet analyzed using Ansys simulation. This is called gas-liquid two-phase flow analysis. The two images on the left are examples of two-phase flow analysis. The y=0 line near the center of these pictures is the original position of the liquid surface, and it simulates a situation where the water is filled with virus. This image shows the results for 35 seconds and 70 seconds after the water has started to flow, and you can see that the virus has dispersed to the top of the y=0 liquid surface. Thus, it's possible to estimate the risk of viruses spreading in the liquid depending on the way toilet water is flushed. Let's move on to see some case studies in detail. The first one is about social distancing. What we are studying here is the behavior of breath caused by coughing, sneezing, and breathing. For example, it's possible to determine whether the breath reaches someone near you or not based on the distance. In other words, we modeled the droplets contained in the breath as particles and verified the possibility of droplets reaching a target. The results obtained include the effect of the breath on the object depending on the wind direction and distance, and the distribution of droplets that affect to the object. This video was created by Ansys and it's available on YouTube. You can search for it using these words: COVID-19, leave additional space when exercising. This analysis suggested if the runners are 1.5 meters apart or running side by side but slightly behind each other, there is a risk of droplets exhaled from the person in front will affect the runners following them. Therefore, it's important to keep a reasonable distance while running, but remember not to run directly behind each other as well. Here's a video of another case study. This is similar to the previous one, but it visualizes the behavior of droplets at a distance of about 1.83 meters outdoors with no wind or with a light wind. This time we also visualize the dispersal of droplets when wearing a mask. So when there is no wind, analysis shows that the droplets attaching to the face and chest of the person standing across from them. When there is a gentle breeze, we can see that the droplets are dispersed further away under the influence of the breeze. As you can see, the droplets reaches a person across the streets even at a distance of 3.11 meters. So what would happen if you were wearing a mask in slightly windy conditions? So you can see that as well in this video. The effect of a mask actually is to suppress the dispersal of droplets and reduce the risk of them scattering to other people. Next one is an example of spray cleaning. Cleaning is another way to prevent COVID-19 infection. This case study simulates the cleaning of a rinser. The analysis shows how cleaning liquid is sprayed up from the bottom to clean the inside of the rinser. In this case, we can see how the droplets affect the object depending on the spray angle and distance from the object. And we can also use the liquid film model to take into account the thickness of the liquid to confirm that it is applied evenly. The results obtained can be used to check the uniformity of application by spraying, to determine the dependence on spray direction, and also to determine the percentage of adhesion by distance. Here are the actual analysis results. Particles of various particle sizes, represented by different colors here, spewed upward from the nozzle. The analysis was performed under 3 conditions: spray angle of 5 degrees, 10 degrees, and 2 5 degree sprays in different directions. The contours show the thickness of the liquid film. There is almost no difference between the 5 and 10 degree jetting angles, but the 2-direction jetting angle results is an uneven liquid film, indicating that some areas are not being cleaned properly. This is another example of spray cleaning by using the liquid film analysis function. It is also possible to represent disinfectant liquid dripping. A hand model is being used, as you can see on this slide, and it's possible to see how the liquid film is gradually distributed under the influence of gravity from a state where the liquid film is applied uniformly to the entire arm. As you can see, the liquid film gradually becomes thinner on the upper part and thicker on the lower part. The next case study is for ultraviolet sterilization. This example uses not only safety but also optical analysis. Co-simulation is actually one of the strengths of Ansys. LED for sterilization are placed in the flow channel and irradiated with light. Sensitivity analysis by material, lamp power, and flow rate is also possible. The results obtained show that flow field inside the device and the optical distribution caused by light irradiation. And disinfection efficiency, which is customized by using a user-defined function, can be added as evaluation factor. This is a detailed overview of how the analysis is performed. First, an optical analysis is carried out and the UV radiance distribution is obtained as text data. The data is then imported into the fluid analysis as the UV radiance distribution. The result is that, for example, the red line is the fluid flow and the purple areas represent high and low UV irradiance. The fluid will flow around the container in this way, sometimes in areas with high UV radiance and sometimes in the areas with low UV radiance. In this analysis, the amount of UV radiation is calculated by adding up the amount of UV radiation that the fluid has received before it's finally discharged. Here is the final distribution of UV radiation. The horizontal axis of this graph shows the infrared irradiation amount and the vertical axis shows the relative frequency. The right side of the graph shows the sufficient irradiation amount and the left side shows the ratio of insufficient irradiation where the sterilization is not completed. Under the design conditions shown here, the percentage of the irradiation amount not exceeding the standard irradiation amount for sterilization is high, indicating that there is room for improvement. Therefore, in this case, as an optimization, we try to install LED reflectors and increase the reflectivity of the circular surface inside the equipment. As a result, you can see that the graph on the right hand side shows that the UV radiation amount has improved. The next story is on sterilization of equipment. This is an example of analyzing the increase in temperature and pressure over time when high temperature steam flows into the equipment for sterilization. The results obtained include visualization of temperature and pressure increases over time, visualization of temperature differences by location, and visualization of sterilization rates by user-defined functions. Here is a view of a sterilizer. To improve the efficiency of sterilization, the temperature difference between individual parts of the device and the temperature distribution in the space inside the device are important. By conducting fluid analysis, we can visualize the temperature distribution in the individual parts of the device and the space as shown here. These analysis results show that the temperature differences inside the equipment is very small at 0.6 Kelvin, indicating that the model here has achieved temperature uniformity. Although this result shows a relatively small temperature distribution, there may be cases where the temperature differences become large depending on the flow rate or the amount of heat. In such cases, the simulation model can be used to verify various ideas for optimization. This case study is for face masks. Basically, this case study visualizes the presence or absence of leakage from gaps due to the face mask's shape, evaluation with and without clasps, and airflow, etc. As shown in this video, we can confirm that a slight change in the shape of the mask can significantly change the airflow. It's also possible to examine how much breath leaks through the gaps and how the pressure loss changes depending on the shape. This step is actually an instructional analysis to simulate the force applied to the face when wearing a surgical mask. As you can see in the picture here, wearing a surgical mask for a long period of time can cause skin irritation. This analysis shows the force applied on the face by the mask depending on the shape of the mask. As you can see, analysis helped to equally spread the force applied to the skin as much as possible to reduce damage to the skin. Next one is an analysis example of a mixing tank. Mixing tanks are often used by chemical and pharmaceutical manufacturers for chemical synthesis and other applications. Fluid analysis technology can be used to visualize the flow field inside a mixing tank to determine mixing efficiency and collect data necessary for scale-up. The example shown here is an example of using simulation technology to verify the impact of increasing the size of a mixing tank from 20 liters to 20,000 liters. In this way, simulation can be used to predict the performance of a giant mixing tank without actually building one. This is a very interesting and popular analysis example to observe ventilation performance. This example shows the prediction of ventilation performance by a ventilation system inside a building. In this case, it's possible to not only visualize the flow field, but also to identify areas of stagnant air using the concept of air edge. By performing this type of analysis, it's possible to calculate the efficiency depending on the placement of air conditioners and exhaust vents, the difference in efficiency depending on the inflow momentum and temperature, and the difference in ventilation efficiency depending on the placement of the ventilation equipment. The animation on the left visualizes the flow field when 6 inlets are placed on the ceiling and outlets are placed on the sides. And you can see how the flow is stagnant and unbalanced due to the influence of furniture such as tables and cabinets inside the room. Finally, let's look at another analysis of ventilation performance, but this time we are visualizing flow fields inside public transportation like airplanes and trains. In this analysis, you can see the scattering of droplets inside the train. An inlet is installed on the top of the train and an outlet is installed at the bottom. And we can verify how the appearance of splashes changes depending on the presence or absence of a mask. You can see here how scattering of droplets is suppressed by wearing a mask as well. So with that, we are reaching the end of this webinar. We explained why CFD is effective for fighting COVID-19 and introduced several examples of simulation to support new normal. COVID-19 is gradually becoming a part of our lives, but it's still necessary to contain the spreading. That can only be done by continuing to improve countermeasures. I hope that the analysis examples we showed today would have given you an idea about how Ansys CFD and other simulation technologies can be utilized to develop and optimize preventive measures during pandemic situations. So we will reply to any questions after the webinar by email. If there's anyone who could not drop their question in the chat, please send an email to information@cybernet.asia. So with that, we have come to the end of today's webinar. I hope you found it interesting. If you have any questions about this webinar or the analysis cases that we presented today, or even about any other Ansys simulation technology solutions for that matter, please feel free to reach out to our team. You can call us, send an inquiry using the web form on our website, www.cybernet.asia, or even send an email to information@cybernet.asia. Thank you.